Glass panes were perhaps the most important technological advance in the history of buildings. They allowed an extraordinary leap forward the quality of indoor life. No longer was the forced conjunction of light and outside air, cold in winter and hot in summer, which had to pass through the same openings. And not just light without wind, the sun penetrating through the glass also heat the room. More in detail, solar radiation incident on a glass surface is partially reflected, partially absorbed, and partially transmitted. Of the absorbed energy, a part returns to the outside and a part is released inside, due to the heating of the glass. However, the fraction of solar energy transmitted does not correspond to the fraction of light transmitted. This is due to the fact that glass transmits all wavelengths of the solar spectrum, not only the ones contained in the visible spectrum. For example, in this image, according to the type of glass, we can see that the amount of transmitted solar energy is different from light transmitted. Due to the introduced selectivity of the glass to radiation, glass caused the so-called greenhouse effect. The glass transmits short and near-infrared waves, but blocks the long waves. Short and near-infrared waves pass through the glass and are absorbed by surfaces and objects inside. These objects warm up and re-radiate long waves, which are blocked by the glass and retained in the indoor environment, generating a temperature increase. In order to better understand the glass properties, a simple energy balance of a glass pane is described, in which the total energy flux through the glass is equal to the sum of A. The solar radiation flux transmitted through the glass. B. The fraction of incident solar energy flux absorbed by the glass and transferred inside. And C. The thermal flux due to the difference in temperature between inside and outside. The instantaneous energy balance can then be written as shown. Tau is the solar transmission factor of glass, function of the incident angle of solar beam and diffuse radiation. IT is the total solar irradiance incident on the glass in watt. And I represents the fraction of solar energy absorbed by the glass and released into internal environment by radiation in the far infrared and convection, given by the ratio UGL over HO, where UGL is the overall heat transmission coefficient of the glass, expressed in watt over square meter Kelvin, and HO is the external surface heat transfer coefficient in watt over square meter Kelvin. Generally, for a 3 mm clear glass, Ni can be considered a constant and equal to 0.26. Finally, alpha is the absorption coefficient of glass. Tho is the temperature of external air. Ti is the temperature of internal air. Since the terms A and B are linked to solar radiation, while C exists even in its absence, the equation can be written in this way, where SAGC is the solar heat gain coefficient, characteristic of each type of fenestration, which varies with the incident angle. A greater value is generally preferred in solar heat applications to capture maximum sun, whereas in cooling application, a low SHGC reduces unwanted solar heat gain. It should be noted that the ideal glass should be capable of transmitting mainly the radiation in the visible range, leaving the spectral distribution unchanged, so as to ensure the same color perception that would occur in the absence of glass. In the cold season, the ideal glass should be also able to transmit the near-infrared fraction of solar radiation indoors to contribute to space heating, and it should be able to block the far-infrared radiation emitted by heated room. In the hot season, by contrast, the ideal glass should be able to block the near-infrared component of solar radiation to reduce the heat gain and transmit the far infrared radiation emitted by the interior space. In this image, transmission coefficient related to each different wavelength of several types of glass are shown. In principle, in hot climates with high solar radiation, such as in the tropics, the ideal would be use glass with low SHGC. This would apply if the properties of the glass were those of the ideal glass. Unfortunately, real glass with low SHGC also shown poor light transmission, which forces occupants to use artificial lighting. Tinted glass, in fact, change the solar spectrum. If the glass is bronze or gray, light quality is little altered and the low light transmittance leads to a high windows to wall ratio, which outweighs the benefit of low SHGC. In order to alleviate the problem of high solar gains in buildings with large windows areas, a type of spectrally selective glass has been developed, which has the capability of attenuating the infrared component of the solar spectrum while maintaining a good transparency to visible radiation. However, due to the low emissivity which characterizes this type of components, spectrally selective glass is extremely positive in cold climates and seasons, but unsuitable in hot climates and seasons.